Hello everyone, this is Saifi here. In the interest of time, let's get started. This slide shows the trend and timeline of LPDDR SDRAM. As is the case with the DDR standards, speed and bandwidth typically doubles for every generation of SDRAM. We have come a long way from, from LPDDR1, and believe it or not, LPDDR2 is still in production, and so is LP3. LP4 and 4X are mainstream today, but it will be replaced by LPDDR5 by 2023. As compared to LP4, LPDDR5 offers 50% higher bandwidth at almost 30% less power. That's pretty impressive. Currently, LPDDR5 is defined till 6400 megabits per second, but there is also a speed push planned, and it will take the speed all the way till 8400 Mbps. Main target applications for LPDDR5 are smartphones that can support 8K video recording, multiple cameras, as well as multiplayer gaming. IoT and automotive are also going to be major applications for LP5 along with tablets and laptops. Next few years are indeed going to be very exciting. Okay, so what's new in LPDDR5? There are plenty of changes. First and foremost, the data rate is higher. It goes all the way till 6400 megabits per second. There's also a speed push planned, which will push the speed till 8400 megabits per second. This new version will be called LPDDR5X. One of the biggest changes is the multi-clocking architecture. We have a separate clock for CA, writes and read burst. And we'll talk about this change in next few slides. The VOH is 250 millivolts as compared to 300 or 360 millivolts back in LP4. And our voltage levels are variable. Another important change is that CA bus is DDR and it's a higher pin count, 7 pins compared to 6 pins in LP4. There are no ODT or even the CK pins are gone. It's all command based. The RX I mask is hexagonal, it's not rectangular anymore. And this is something new. We have a non-target on determination enabled for DQR, DMI, and RDQS. This was not present in LPDDR4. Another big change is that in the DRAM RX for DQs, we have equalization. This is something new for LPDDR5. We have one-tap DFE. We also have a WCK duty cycle adjuster and monitor to improve the WCK duty cycle. You have programmable multi-bank organization and also link ECC to increase the robustness of the channel. Both RX equalization as well as link ECC are optional features. We have a few power saving features like deep sleep mode and DVFS-C and DVFS-Q, which is dynamic frequency and voltage scaling. And we also have auto refresh and PASR, which is partial array self-refresh. So let's talk about the clocking architecture in LPDDR5. This is one of the biggest changes as compared to LP4. Now this clocking architecture is very similar to graphics DDR5. So if you have worked on or are familiar with graphics DDR5, then this should be a piece of cake. Before we deep dive into LP5 architecture, let's just revisit LP4 architecture for a moment. It is pretty straightforward. Clock is unidirectional, and data strobe and data are bidirectional. And CA bus is tightly coupled with clock. And notice that it's SDR. Now let's take a look at LPDDR5. Now clock is the same. It's flowing in one direction from SoC to LP5 DRAM. But notice that your DQS is broken down into two separate clocks. We have a WCK write clock and our DQS, which is read data strobe. They are both unidirectional. Data is again bidirectional, same as LP4, and so is CA. But the important change here is CA bus is DDR, it's not SDR. So let's just take an example like what we have right now. For a max data transfer of 6400 megabits per second, a write clock is running at 3200 megahertz. That's the max speed defined in LPDDR5. Now, since you have a separate clock for CA and separate write clock, these two are synchronized and they operate in a ratio which can be 2:1 or 4:1. Typically above 3200 megabits per second, the DRAM will be in 4:1 mode. What that means is WCK will be 4 times faster than clock. So for this particular example, since WCK is running at 3200 megahertz, your clock can only go up till 800 megahertz. So your pretty much your clock is maxed out or is capped at 800 megahertz. Now what does this do to CA bus? Your CA is tightly coupled with clock, and since clock is running at 800 megahertz and CA is DDR, your CA data transfer is 1600 megabits per second. So even though it's DDR, it's running at a lower speed as compared to LP4. So this makes it easier to close timing and improve margins, and it's a big enabler of higher speed in LP5. So why do we need WCK-based clocking? LPDDR5 SDRAM uses WCK for a couple of reasons. First one is to capture the right data from the SoC, and the second one is to generate RDQS and push out DQ on the read path. Now, this was typically done by clock in LPDDR4. So as you can see from here, the path between clock buffer and DQ pad is quite long as compared to LP5. According to one study done by Samsung, this reduces the PSIJ, which is power supply induced jitter, by 40% and improves the read window by 15%. This is one of the key changes that enables max data transfer of 6400 Mbps. LP5 SDRAM has WCK running at 4 times or 2 times faster than clock. Now, inside the DRAM, the internal circuits on WCK clock domain are running much slower as compared to WCK. Now, this is typically achieved by having a clock divider in the WCK clock tree. Our problem is that the initial state of WCK divider is not known, or is rather unpredictable. Also, during the idle state, that is in between burst, WCK goes in high Z state to save power. This is typically achieved by turning off WCK drivers on the SoC TX and the buffers on the SoC on the DRAM RX. Now this again puts the WCK divider in an unknown state. It could either be aligned with CK or it could be misaligned. There's no way of knowing that. Therefore, memory controller must synchronize or align WCK with CK with clock before issuing any read or write command or even any training operation. Controller starts this WCK to sync process by initiating or issuing a CAS command. And once this CAS command is issued, a controller needs to send out WCK in a fixed pattern or sequence. WCK needs to have a static region, a half rate toggle, and full rate toggle. So let's take a look at a sample LP5 waveform. This is your WCK, and this is your corresponding data. The settings used are WCK to CK ratio is 4:1. Your preamble is broken down into two parts, static and toggle. They both are 2TCK long. Your postamble is 2TWCK. Notice that the postamble is with respect to write clock and preamble is with respect to clock. So WCK is in high Z state till here and then it starts toggling. You have a static region of 2TCK and then you have a preamble toggle which consists of a half rate clock and a full rate clock. Now, half rate is done to reduce the ISI and relax the timing requirements for WCK to CK synchronization. As a test engineer, you want to find out which is the first valid strobe edge, because typically you want to ignore all the data that, for the preamble cycles. Now, this WCK to CK routine makes it a little bit challenging to find out this first valid strobe edge, because for each frequency bin, the preamble and postamble have different requirement, and it makes it a little bit complicated uh, to, to, to figure out which one is the first valid strobe edge. There are two options which a controller can use to synchronize WCK with CK. First one is dynamic, and second one is WCK always on mode. In the dynamic mode, WCK needs to be synchronized with CK before each and every read and write operation. It's less power optimized. It affects the performance as well, since WCK synchronization takes several clock cycles. Now, there are three versions of CAS command that can be used to initiate WCK to sync operation. CAS fast sync, CAS write command, and CAS read command. These two commands, write and read, are optimized for the particular operation. CAS write command is optimized for write operations. CAS read command is optimized for read operations. So after issuing this write command, a controller has to follow up with the write command. After issuing a CAS read command, a controller has to follow up with a read command. The fast sync, however, is a more global command. It can be issued simultaneously to multiple ranks. Also, after this command is issued, controller can issue pretty much any command. It is not limited to issuing just a read or write command. Now, this added flexibility comes with more power usage. This command is less power optimized as compared to CAS write or CAS read command. In WCK always on mode, once the synchronization is done, the SoC memory controller will keep WCK toggling at its full rate, regardless of the DQ operation. Now this mode offers better performance since we don't need to synchronize WCK with CK before every read and write operation. But since WCK is always on, needless to say, this mode eats up a lot of power. So to summarize, a memory controller needs to make a performance versus power trade-off in selecting WCK to sync up options. Now let's talk about LPDDR5 training modes. There are a bunch of trainings, and all these trainings are typically done during boot up. A lot of these trainings are exactly similar as what we had in LPDDR4, like command bus training, write leveling, read and write data training, read window training, and so on and so forth. But there are a couple of new trainings which are very specific for LPDDR5. One of them is WCK DCA training. Now, as LP5 SDRAM has a duty cycle adjuster and monitor inside the WCK clock tree. And what this training will do is it will try to compensate for any duty cycle error on WCK. This is typically done to make sure your RDQS, which is generated from WCK, has optimal duty cycle as well. Your DRAM DFE training will adjust the one-tap DFE to improve the write eye margin. In this slide, I quickly want to highlight few features that improves the performance of LPDDR5 SDRAM. They are multiple clock architecture. We talked in detail in previous slides. We have 3 frequency set points as compared to 2 in LP4. We have a duty cycle adjuster and monitor that improves the duty cycle of WCK inside the DRAM. And we also have optional link ECC and one-tap DFE to increase the robustness of memory channel. Now this slide highlights the features that are supposed to save power in LPDDR5 SDRAM. We have a bunch of new features that were not part of previous protocols. We have a DCF or data copy function and write-x feature, which is supposed to reduce the data transmission on the DQ bus. When a controller issues a DCF or data copy function, it will only transmit data on one pin instead of all the pins, all the DQ pins. Now SDRAM will copy data transmitted on this single pin to all the other IO pins. For the write-x function, SDRAM will write zeros or ones to a specific memory address. SoC again does not need to send in zeros or ones. We have a DSLIP mode. In this mode, SDRAM will turn off all the processing except for self-refresh. We have a newly defined single-ended mode. In this mode, you have an option to select all the differential clocks and use it as a single-ended signal. You also have DVFSC and DVFSQ. DVFSC is dynamic voltage and frequency scaling for core and IO, and allows you to switch between different voltage levels and thereby save power. LPDDR5 brings in variable voltage levels. The core 1 supply VDD1 is set at 1.8 volts, no change in that. But your VDD2 is being split into high and low supplies. 2H is set at 1.05 volts and 2L is set at 1.9 volts. Your IO supply, which is VDDQ, is not split per se like VDD2, but you have two ranges, and range 1 is set at 0.5 volts and range 2 is set at 0.3 volts. So depending on the data transfer speed and the termination and untermination case, you can a controller can switch between zero point 0.3 to zero point 0.5 volts. So if we look at from the perspective of termination and try to figure out what the VOH would be, you will see that for terminated case, your single-ended VOH will be half of VDQ. And for an unterminated case, your VH will be same as VDQ. So this brings in additional complexity in testing. You need to test for all these modes. Because if a system is going to operate on the fly and switch between power supplies, we need to make sure that these settings are tested and stable. As you can see in this block diagram, in a typical dual rank configuration, the DQ pad is shared between two dies. Let's call this rank 0 and rank 1. Rank 0 is the target rank, and rank 1 is a non-target rank. So when the SoC TX is driving the data towards rank 0, which is our target rank, then this path towards rank 1 acts as a stub, and this stub causes reflection. This degrades the signal integrity. To overcome this problem, LPDDR5 supports non-target DRAM on-die termination for DQ, DMI, and RDQS pins. So this was not present for LPDDR4, but you will have a non-target on-die termination for LPDDR5. This improves signal integrity in the dual rank configuration and also enables SDRAM to operate at a very high data rate. In LPDDR5, there is an option to use all the differential clocks in a single-ended fashion. This is typically achieved by putting the DRAM in a single-ended mode. This is done through mode registers. What this means is only one leg of a differential clock can be turned on, whether it's true or complement. This mode can be enabled at a lower data rate. It's a power saving feature. And in this mode, to further reduce the power, on-die termination for target and non-target ranks for all critical signals has to be disabled as well. So it's also called something called strobeless mode defined. Now, in the strobeless mode, RDQS is completely switched off. DRAM will only send out the data to the SoC. There won't be any RDQS. So now the question is, how does the SoC latch this incoming data? Well, in the strobeless mode, SoC5 will use an internal clock to latch this incoming data from the DRAM. And since the clock strobe is internal to the SoC, our next question is, how do I test it? Can I even test it? Well, it's going to be very difficult, if not impossible, to test this mode. This clock, internal clock, needs to be brought out on an external pin somehow, and it needs to be aligned with the data. Until that can be done, this mode cannot be tested. There are also some restrictions placed in JREC in the spec on what signals can be enabled in this particular mode. So for lower speed rate, which is lower than 1600 megabits per second, only clock 2 can be enabled. But we have an option of enabling either write clock, true or complement, and in the same way we have an option to enable either RDQS, true or complement. The last row signifies the strobeless mode, where RDQS is completely switched off, and WCK and CK are both in a single-ended mode. The rectangular mask on LPDDR4 is replaced with the hexagonal mask on LPDDR5. RX mask is defined by TDI-VW1, TDI-VW2, and VDI-VW. It's centered around the VREF. Also, LP5 uses an unmatched WCK and DQ path inside the DRAM die. The WCK path is much longer compared to DQ. So that means like when you're probing at the DRAM ball, uh, the WCK and DQs will not be center aligned. However, they will be center aligned at the internal latch. So this is pretty much the same concept as LP4 4X. However, there is a new parameter called TDQ to DQ that is being introduced, which essentially measures delay between two DQ signals. Applies to CA as well. So just something to keep in mind when you're designing your interposers. If you want to measure this parameter, then do bring out 2 DQs per byte or multiple CAs. Any of the previous LPDDR SDRAMs didn't have any RX equalization whatsoever, but LPDDR5 supports one-tap DFE. This one-tap DFE will improve the RX margin, and it will be used to open up the eye at higher speeds. It can be independently programmed for each rank and byte. And another thing to keep in mind is that when DFE is enabled, DQ needs to be driven low for 2UI before the start of actual data. Now, this is typically done to precondition the DFE circuit. For LP5, DFE is optional. So depending on the channel characteristics, one might not even need to enable DFE, even at max data rate of say 6400 megabits per second. But for LPDDR5X, which is supposed to go all the way till 8400 megabits per second, it might become mandatory. So watch out for this thing in future. Let's look at some of the challenges that a engineer would face while testing LPDDR5 DRAM. Signal access and probe loading. Now these two are kind of interrelated. A typical way to probe a DDR interface is by using an interposer underneath the DRAM along with high impedance probes. Now it's getting harder and harder to access signals on the interposers, especially if they are right next to each other. Also adding probes and interposers, they act as an additional load on the DDR bus and deteriorates signal integrity. Test coverage. Now LP5 introduces a whole range of new features, and few of these features like DVFSC, DVFSQ, and single-ended mode needs to be thoroughly tested. Oftentimes I've seen that we only focus on the testing efforts on the max data rate and ignore the lower data rates completely. But as a matter of fact, almost 80% of a memory usage in a smartphone happens to be in the mid-speed range, which is typically between 800 megabits per second to 1600 megabits per second. So I mean, think about it, right? I mean, we don't always watch a video or play games on our phone. I mean, I hope not. Typically, we are checking the email, texting, browsing, reading news, and so on and so forth, which doesn't require max data transfers. So it is critical to make sure that device and subsequently the system is tested for above new modes. De-embedding will become absolutely critical for LP5. For LP3 and LP4, speed was fairly low, memory had tons of margin, and de-embedding for the most part was kind of like optional. But for LP5, it will become absolutely critical to correctly apply the proper deembedding techniques, even more so at the max data rate. Next challenge that we will face is a bus separation. Now, this has been traditionally a pain point for all previous memory generations. Even in the good old days where we had writes were center aligned and reads were edge aligned, even in those days we had problems with the memory bus separation. Well, there is no good news here. This will continue to be a problem even for LP5. DRAM RX equalization, in this case 1-tap DFE. Well, as a test engineer, we want to probe as close to the RX as possible. We want to see what the RX is seeing. But if there is a lot of RSI in the channel and if DFE is enabled, then the RX is hiding behind the DFE engine. And furthermore, DFE by nature is a closed loop system that requires a continuous pattern, while DDR by nature is a busty environment. So this is going to be a problem to incorporate one-tap DFE in our testing solutions. And lastly, debug. Higher data rates and faster signal speeds mean complex design and even more complicated test procedure. This will push the boundaries of signal integrity. It will make the testing more challenging and more complicated, and our debug tools need to be faster, smarter, and more efficient than ever. Having said that, let's go over a few of these test challenges and see how Tektronix can help alleviate some of these pain points. So, with signal access, everything is getting smaller and smaller. Accessing the DDR bus is getting harder and harder. Oftentimes, when you put the interposer and probe on the DDR bus, chip doesn't even boot up. You're probably aware of this already on LP4, and LP5 is just going to make it worse. Tektronix recommends using P77 tri-mode probes. This probe supports multiple different probe tips for different use cases. And all these probe tips have an active buffer tip design, and it offers industry's lowest probe loading. It also supports tri-mode functionality. Tri-mode on this probes allows you to probe single-ended as well as differential signals with the same probe setup. You don't need to desolder the probes to do that. This can come in very handy to test the single-ended mode in LP5. For the interposers, I highly recommend using edge probe interposers from Nexus. They are the same size as the DRAM component. It fits on any board and it doesn't need riser. It's awesome. De-embedding. First of all, before we begin, I would like to congratulate all the engineers who haven't had to deal with de-embedding yet on a memory subsystem. You guys have been very lucky. And for the rest of the folks who had the pleasure of using de-embedding, please accept my deepest condolences. You already know how painful it is to set it up and get it right. Having said that, let's jump right into it. So what is de-embedding? Now, de-embedding is a technique that we use to remove the effects of probes and interposers. Not only that, we also use it to move the probe point from DRAM ball to DRAM die, something called virtual probing. The idea is to minimize reflections and see what the actual receiver is seeing. Now, In order to correctly apply de-embedding for both read and write cases, we need to faithfully represent the channel. One of the ways this can be done is by using S-parameter models of SoC package, DRAM package, boards, interposers, and probes. We also need to know the TX drive strength and RX on determination values. So conceptually, de-embedding is very simple, but implementing it correctly is not that easy. Problem is that we need multiple S-parameter files and they all come from different sources. Any one mistake in any of these files will give you an incorrect result. It's a classic case of garbage in, garbage out. And the sad part is that you won't even realize that it is wrong until you look at the final output, which is the de-embedded waveform. At this point, you will start debugging the issue, and it can take a lot of time. Trust me on that. Okay, so enough of challenges. How can we make this process better? Well, a magic wand would be nice. Just wave it and be done with it. Sorry, we don't have one. But what we have is a tool called SDLA, Serial Data Link Analysis. SDLA is a very powerful tool. It is used for de-embedding and RX equalization. It allows to validate the quality of S-parameter files upfront. Also helps to remove the effect of probes and interposers. You can resample the S-parameter file, you can check passivity, port assignments, and most importantly, it has an amazing and powerful plotting capability. You can plot S parameters, impedance profiles, Smith charts, and a lot more. And doing this at the very beginning gives you the peace of mind that all your S parameter files are okay. This is a huge plus. It also supports 2-port, 3-port, 4, 8, 12, and even 16-port models. And if you don't have S parameter models, you can use RLC, basic RLC models, or even create your own transmission line parameters and get started. So all in all, SDLA makes de-embedding process, I wouldn't call it easy, it makes it bearable. It makes the debug go a lot faster and efficient, which saves a lot of time. This is very critical when you are on a schedule. Read-write bus separation problem. Similar to LPDDR4, writes are not center aligned. There is a fixed offset between WCK and DQ. However, having a dedicated strobe for reads and writes does make it easier, a little bit easier to separate the reads and writes. But now we have to deal with WCK to CK synchronization. As I mentioned earlier, our WCK preamble now consists of static, half rate, and full rate toggle that needs to be dealt with during bus separation. Now, Tektronix Tech Express LPDDR5 software application has built-in new algorithms to separate reads and writes. We offer read-only mode, write-only mode, and on top of that, we also have a read-write burst mode, which you can use if you have a bidirectional traffic on the DDR bus. Burst reduction is based on a bunch of factors to improve accuracy and make it more robust. It takes into account amplitude, preamble, postamble, and burst length. In fact, the app itself has a lot of customizable features and it's very fast. It will cut down your test time in half. We have a small demo planned at the end of this webinar. so you can see it live in action. As I mentioned earlier, debug will become a big part of LP5 validation. Challenge that most folks face is how do I debug system failures? Or what do I do if something fails in the compliance app? How do I debug it further? We at Tektronix realize that there is no one way to test memory subsystem. Test cases varies from company to company, team to team, product to product, and application to application. So we have put in a bunch of new debug features in our compliance app. In fact, we constantly want to evolve in this field and keep on making enhancements which will improve a user's workflow. I have highlighted a few of the debug features here. First one is the user-defined acquisition mode, which you can see right here in our compliance app. This is a highly advanced mode, and what this mode does that is that it puts the control back in the hands of user, where it should have been to begin with. It totally allows the user to customize the scope settings like bandwidth, record length, sample rate, the scales, the horizontal and vertical scales, and a lot more. We also have a new feature which allows you to save the waveform during runtime. Now, most compliance apps, when you select a test and hit start, they will start with the default setup, will do the auto set, and then they will go and make the measurements and provide a report. This is excellent and fine if everything is passing. But what happens when something fails? How do you debug it? With this feature, the save the failing waveform feature, you can actually save the failing waveform during runtime. Let me give you a small example of how this feature will be useful. Now, let's say you selected a test, and to run that test, you want to capture 1 million UI. That's a lot of UIs. And depending on the traffic on the bus, scope might have to acquire multiple times to get to that 1 million UI. Let's say the scope has to acquire, say, 8 times. And out of those 8 times, failure only happened in the 6th acquisition. This particular feature will let you save that 6th acquisition on the scope. Once the test is done, you will get your report, but it will also save that failing waveform that you can recall later on and debug it further. You can rerun the compliance app on that failed waveform. You can go to our DPA-Jet software and run some non-JEDEC parameters to gain insight into the failure. Very powerful tool, very powerful feature. We also realized that plotting in I is an important part of SI validation. So we have put a bunch of customizable features which gives you more flexibility and more power when you're plotting the I. Some of them are stop on masthead. You can select the number of UIs. You can even include the margins in the plot itself. You can customize your RX mask, and you can scale the I with respect to the data or clock. By the way, how are we doing on time? We're almost approaching our time limit, and I just realized that I have talked a lot and possibly have caused an information overload. I'm sorry for that. LPDDR5 is a broad topic. But this is my last slide for today, I promise. No more talking. I just want to provide a quick summary of our solution. This software application was designed with you in mind. It was designed to improve the workflow and make your life easier. I highly encourage you to check it out. Coming up next is a short demo by our memory application engineer, Joseph Swilland. Over to you, Joe.